Okay, so we were talking about rubidium, strontium and samarium, neodymium systematics. But before we have talked about how the isochron equations are written, and now I will put in some values. These values are put before, but I will again put these values before we go into the final concluding part. So I'm drawing again the partition coefficients of rubidium and strontium in olivine, orthopyroxene, clinopyroxene, garnet, plagioclase and amphibole, and this is 0.010, 0.022, 0.031, garnet 0.042, plagioclase 0.071, and amphibole 0.29, and the value for strontium is 0.014, 0.040, 0.060, 0.012, and 1.830 and 0.46. This is for rubidium, strontium, and for samarium and neodymium the values are 0.007, 0.050, 0.445, 0.102, 0.039, and 1.804, whereas the value for neodymium is 0.006, 0.030, 0.230, 0.026, 0.055, and 1.340. These are the pairs that we are talking about. Now, you can see that if you take rubidium, this is the crystal melt partition coefficient of elements, rubidium between olivine and melt. This we have done before. I have given you the whole, this thing I didn't give you for, so it's all well known. But the important point here is, this value is higher between rubidium and strontium. This value is higher for orthopyroxene. This value is higher for clinopyroxene. This value is higher for plagioclase. And this value is higher for amphibole. Right? So, except for garnet, strontium has a higher value than rubidium. That means rubidium for the mantle rocks, rubidium for the mantle rocks is more incompatible. That is the final result. Rubidium is more incompatible than strontium. That is important. Rubidium is more incompatible than strontium. But if we take samarium and neodymium, between these two, samarium is higher, 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 and higher. So that means neodymium is more incompatible than strontium, than samarium. So, this is something interesting. Rubidium is more incompatible than strontium, Both are incompatible, but rubidium is more incompatible. So if you melt the mantle, rubidium will be partitioned into the melt more favorably than strontium. Both will be partitioned into the melt, but rubidium will be partitioned more in the melt relative to strontium. It is important to tell you right at this here that rubidium element, we are talking of rubidium element, and one of the isotopes that make up rubidium is rubidium 87, which is the parent. Have you understood? Now, the amount of rubidium, say for example, if you look at the periodic table, a good periodic table, it will never give you the atomic weight of oxygen as 16. It will not. It will give you the value 15.997, not 16. Why? Because oxygen is made up of oxygen, 18 oxygen, 16 oxygen, 17. Their proportions determine the total amount of oxygen. That is important. Similarly, the element rubidium consists of both radiogenic and non-radiogenic rubidium, and there are several isotopes. So these isotopes together, they make up total rubidium, right? Element rubidium. So here, element rubidium is more incompatible than strontium, and rubidium happens to be the parent of rubidium-strontium decay, right? Here, samarium and neodymium, we have said that neodymium is more incompatible than samarium if we just leave aside plagioclase. That means if you melt, neodymium will be preferentially transferred into the melt, or samarium will be partitioned into the mantle relatively, because samarium has a higher value. So in the melt, neodymium by samarium would increase, but in the solid, samarium by neodymium would decrease. Which would mean to say is, samarium, the samarium, which is the parent, from 147 samarium is the parent. Again, all the isotopes of samarium make up total elemental isotopes, samarium. So here, neodymium is more incompatible than samarium. That means, here you see neodymium is the daughter. Samarium is the parent. So here, the more incompatible element is the parent. More compatible element is the parent. And here, the parent is the more incompatible element. Right? With this information, I will leave this, I will erase this, but leave this important information here. Now I will draw two diagrams. This is 87 strontium by 86 strontium. And this is time. 4, 3, 2, 1, 0. This is time elapsed. I will draw another diagram just below it. So 4, 3, 2, 1, 0. This is 43210. This is billion years. The same axis, 43210. Time in billion years, time elapsed in billion years. And this is, I will draw the dot. Yeah. This is called bulk up. From this expression, at when Earth was formed, at pre, it had this value at 4.55 billion years. When Earth formed at 4.55 billion years, this was the initial 87 strontium by 86 strontium was the initial value. That's how the Earth formed. And if nothing happened, and Earth behaved a closed system, then the Earth should evolve along this line to today. This is what it is. Essentially, from a value close to 0.699 to a value close to 0.702. So you can imagine very small difference from 699 to 0.702. So you can imagine your analysis had to be spot on to identify this difference. Have you understood? So what happens now? I have called this Barbie. The word Barbie, actually you can ask me, sir, how did you get this value? The answer to this question is, lot of meteorites have been dated. Lots of meteorites have been dated, including carbonaceous chondrite, chondrite, many have been dated. And most of the dates in those meteorites can have different ages. I have not covered this topic here because it's way outside this. Meteorites can be bombarded, can be impacted, so they will change. Meteorites can change their system. But several meteorite samples have been dated. And they have found that they have given us an age of 4.55 billion years. And in that 4.55 billion years, that's where it is, regression calculations show that the value corresponds when rubidium 87 by this is 143 neodymium by 144 neodymium. This is what you measure. This is the value. This value has been achieved from different meteorite samples that have been analyzed. And essentially, this particular value comes from, it's called Barbie because it says basaltic achondrite best initial. Basaltic achondrite best initial. So this is value, name is given as Barbie. So this value is taken to be, which is found out, determined from the chondrites, and from lunar rocks, which are 4.55 billion years, that they closely converge to this value. And this is called basaltic achondrite bastonaceous. So if we take this value was the same as that was inherited by the Earth and other planets in the solar system, if it was so, then this is the value from which the Earth started in terms of 87 strontium by 86 strontium, and today it will reach this theoretically if nothing else happens. Similarly, if you take again some 143 neodymium by 144 neodymium at the age of 4.55, this is the value which is close to 0.507. 0.507, a value close to it. You know, isotope people normally calculate value up to 6 and 7 decimal places. It's difficult for me to remember all those decimals, but the value very close to 0.507. And today, the value that you reach is close to 0.512 for samarium neodymium system. And what is CHUR? CHUR, all of you know, is chondrite uniform reservoir. CH, chondrite uniform reservoir. It's called CHUR. So essentially, all these values, the bulk Earth initial values, these are taken from chondritic meteorite, which yield 4.55 billion years. And from rocks, lunar rock samples, for example, which give you 4.55 billion years. So this gives you a value, possibly the whole solar system inherited. And if this was the initial inheritance, or maybe this was the DNA of our Earth, also as a part of the solar system. But you must be also aware that there are a lot of meteorites that have been now dated, have a slightly different age, and they are thought to come from other solar systems, which has been captured by our solar system. We don't go into many of this, but it can be discussed. And this is the samarium neodymium from chondrites, which gives you a particular value. And from this, the bulk are evolved here. Now what happens? Let's say, at 2.55 billion years, let's say there had been a cataclysmic melting event. Let's say, cataclysmic melting event. So what happens at this point on the graphs? At this point on the graphs, at 2.5 billion years, remember this is the Proterozoic Archean boundary we are talking about, 2.5 billion years. Let's say there has been a cataclysmic melting event in which the mantle melted in large parts. And what happened? Obviously there was a melt and a residual melt, like before, and depends upon whether the whole mantle was involved or a part of the mantle was involved, but let's assume there was this event where a melt and a residual solid were produced from an Earth which had this value at this time. This value is not 0.599 here, neither it is 0.702, it is a value in between. Similarly, for the samarium neodymium, it's 0.507 and 0.512, but here the value, say, was close to 0.510. So, let's say this event happened. So, what will happen? Here, rubidium is more incompatible than strontium. So, what happens? If this is so, then rubidium will be, you see, along this line, what is happening? Why is the value increasing this way? The value is increasing this way because more 87 strontium is being produced. Remember, 86 strontium does not change in abundance. More 87 strontium is being produced due to the decay of 87 rubidium. And here the value increases because 147 samarium is disintegrating by alpha particle decay to 143 neodymium. That is the theory. So now, if rubidium is more incompatible than strontium, so rubidium should be preferentially partitioned into strontium, preferentially partitioned into the melt. So what will happen if you partition rubidium into the melt? More of rubidium will go into the melt. That means it will produce more 87 strontium than the bulk arc at this point. Have you understood? Because rubidium is being preferentially partitioned. It is being partitioned, or rubidium by strontium ratio is increasing in the melt. So, and rubidium is decaying, 87 rubidium. So you will start producing more 87 strontium than the bulk arc value. So what will happen? The melt will move in the direction like this. Now, you can ask me, sir, can it do like this? Yes, it will. It will. It can have a different slope. But that would depend on the rubidium by strontium concentration of the material that is undergoing partition melting. Okay, you read about what will determine the slope of this equation. The slope of this equation will be determined by rubidium and strontium ratio of the rock. But anyway, what is important is this is the melt. That means this is the crust. Right? So why is this positive? Why is this here? It is because rubidium over strontium is being relatively partitioned into the melt. So if more rubidium is partitioned into the melt, then more 87 strontium is produced due to decay of 87 rubidium. That is why this would be the direction in which melt of the crust increases. And what will be that of residue? Let's say it could be this, it could be this, it could be horizontal, it could be like this. Which of the three cases will be correct? This is parallel to this. This is 87 strontium, 86 strontium decreasing. This is decreasing. And this one is 87 strontium, 87 strontium, 86 strontium is increasing. Which of these four graphs will be right? Now you see here, 87 rubidium is being partitioned. It does not mean that the solid does not have rubidium. Rubidium by strontium ratio has increased in the melt, but it is there in the solid. So as long as rubidium is there in the solid, but in smaller proportion, it will decay to 87 strontium. So 87 strontium or 87 strontium by 86 strontium will increase even in the solid, because there is still rubidium in the solid. Okay, because rubidium by strontium ratio increased in the melt, but that does not mean that there is no rubidium in the residue. Rubidium by strontium ratio has decreased, but as long as there is rubidium, it will disintegrate into strontium. So what will be these? So all these three graphs, this graph and this graph, means 87 strontium, 86 strontium will increase. No, it cannot. It cannot. There is this graph which is parallel to the time axis. Is it possible? This graph means that the 87 strontium, 86 strontium does not change with time. It is also wrong. It's not possible. So all these three graphs are not applicable. So this graph is applicable. It lies between the horizontal and this is where this will be the melt and this will be the residual mantle. This will be the residual mantle. So if you look at the residual mantle, what will happen is it will have a value which is lower than the bulk arc at any particular time. Lower than the theoretical bulk arc value at that any particular time, and the melt will have a value more than the bulk arc at any particular time. And this ratio, you see here, this and this is a ratio. This is m divided by n. So now I can ask you, what is m divided by m plus n? I will not answer the question. You think about it. What will be m divided by m plus n? This is the bulk arc value. This value is m and this value is n. So if I write m divided by m plus n, what does it mean? You find it. Now that is very important now from the diagram, that if you had melt the mantle or melt the rock, then from the partition coefficients of the constitution of the minerals, you can find out which element is more compatible, which element is less compatible, and you can find out. And for rubidium strontium, rubidium is more incompatible. Remember, rubidium is the parent. Rubidium is the parent. So the parent is partitioned. Remember one thing, there is a common mistake students make while writing. They say 87 rubidium is partitioned. No, it's wrong. Rubidium is partitioned. Now, rubidium contains all the isotopes of rubidium in different ratios. Have you understood? These values are well known in what ratios they exist. 87 rubidium is not partitioned. Rubidium is partitioned, in which 87 rubidium decays to 87 strontium. Then, on melting, isotopes don't partition. Elements partition, not isotopes. But the isotopic ratios are well known. Okay? So remember this, that on melting, isotope ratios don't mass fractionate. Elements mass fractionate. Rubidium by strontium fractionates, but 87 rubidium by 87 strontium does not fractionate. Elements fractionate. So now, if you look at the melts, they will have a value here, and you look at the residual mantle, they will have a mantle value lower than the bulk art. And now we come to 143 neodymium by 144 neodymium. What has happened? Here, what will happen? Remember, neodymium is more incompatible than samarium. That means samarium is, obviously, it's saying it another way, samarium is compatible. That means samarium will be retained in the solid. Opposite of this, remember, samarium is the parent. Here, the parent is more incompatible. Here, the parent is less incompatible. The parent is less incompatible. So what will happen here is just the mirror image of this. So what will happen if you melt a rock at the same point, then what will happen? You can see here, neodymium is more incompatible than samarium. So what will happen? Samarium content will increase in the residual mantle. The samarium content will increase in the residual mantle. That means, if I draw a line, time t is equal to 0, this line will be of the melt extracted mantle. This is the reverse of this. And the melt would have a graph like this. This is the melt or the crust. So you see, the relations are a mirror image of each other. In the melt, you can see the rubidium by 87 strontium, 86 strontium should be higher than the theoretical bulk art. Here, 143 neodymium by 144 neodymium, this value in the melt should be lower than that of the bulk art. For the simple reason that here, samarium is the parent. Thus, the parent, samarium, is less incompatible than the daughter, than neodymium. And here, it is just the reverse. So just imagine here, the melt, the 143 neodymium by 144 neodymium, this ratio will be relative to the bulk art. This ratio will be higher in the melt extracted mantle, or sometimes this is called the depleted mantle. And melt and the crust will have a lower value than the bulk art. But remember one thing, in both the cases, 143 neodymium by 144 neodymium in the melt, and 87 strontium, 86 strontium in the melt should increase. That's one thing. Should increase. Right? Okay. So now, if we do one thing, we combine the two in a diagram. We combine the two. Like say, we plot 87 strontium by 86 strontium. And this is 143 neodymium by 144 neodymium. Let's check. So, now if I say, let's start with the bulk R. In which direction did the isotope ratios of the bulk R change? In which direction? This way, this way, this way, this way. In which direction did the composition of bulk R change from 4.55 billion years ago to today? In which direction? The answer is both 87 strontium by 86 strontium has increased and 143 neodymium by 140 neodymium has increased. So the trajectory from the old Earth to the new Earth, have you understood? From 4.55 to today, the bulk Earth must have changed into this direction. So this was the, say 4.55, this is today. This is today. Why? Because 87 strontium and 86 strontium of the bulk Earth increases with time, and again here 143 neodymium by 144 neodymium increases with time. So the bulk Earth has changed. So at this point here, we can have two diagrams. We can divide this in two ways, 4 halves. 1, 2, 3, and 4. So now, if you melt the mantle today, if you melt the mantle today, where will be your residue? Where will be your residue? Residue means the residual mantle. Where will be your residue? Which direction? If you melt today's bulk Earth, if you do a magmatism of the bulk Earth, so which direction will the melt extracted mantle will be? How do you find out? Here you see 87 strontium by 86 strontium should be higher than the bulk Earth of today. Yes or no? And the melt will be higher, but this one will be lower. 143 neodymium by 144 neodymium should be low. So what we will do with respect to the bulk Earth, so the melts will be richer in 87 strontium, 86 strontium, and poorer than the bulk Earth relative to the melt extracted mantle. So those melts will plot on this side in quadrant 4. They will plot on this side. I'm talking the melts first. Look at the melts. 87 strontium by 86 strontium is more than the bulk Earth. This is the bulk Earth value today. At 2.5 it must have been here somewhere. So the melts will be generated here. And what about the mantle? What about the melt extracted mantle? Here you see rubidium by strontium, 87 strontium, 86 strontium should be less than the bulk Earth. So if it is so, then it should have been less than the bulk Earth. But here, the residual mantle should have a higher value. So the melt extracted mantle should plot here. So the movement should be here. So this is the trajectory of residual mantle. And this composition would represent the bulk Earth composition. The bulk Earth composition. Have you understood? So, once more. Nothing here. This is of no value, this quadrant. What about here? This direction, say for example at 2.5, this would have been the bulk path at 2.5. Say at 2.5, the bulk path 2.5 billion years, the bulk path would have been there. And the same, the melt extracted mantle will plot here and the melts will plot in this direction. But today, since the value has increased, the residual mantle will plot here and the melts will be plotting here. Have you understood? So that is the important one. But this isotopic ratio, today represents the primordial mantle. That means that is the mantle from which there was no mantle extraction. Nothing was extracted. Have you understood? So that is the most important point. At 2.5, this point would have been the bulk path value. This point would have been the bulk path value. So this is very easy to understand. If you have the old crust today, it should be here. Old means also lower crust. I will ask you to find out the reason why. The younger crust would plot here, the younger crust. And this would be the place where you have possibly Phanerozoic crust. Phanerozoic crust. So this would be the directions of the positions of the crust. So the crustal rocks will have higher 87 strontium, 86 strontium and lower 143 neodymium by 144 neodymium, as I have suggested, as has been shown here. So remember this. If you this the bulk path, then the crustal rocks would be plotting on this side and this would be plotting on, and the residual melt extracted mantle would plot on this side. Nothing here. And here you will have the old crust and the younger crust and the Phanerozoic crust. So now if the melts are mixed with this, if the melts are mixed now as they come up, so the contamination would be along this direction. These are the directions of contamination. As the magmas come out, they get contaminated with the different things. Here you have the Phanerozoic sediments, here you have the younger crust, here you have the older crust. So that should give you the directions of contamination of a mantle-derived melt when it comes through the crust, if there is an isotopic exchange. Have you understood? So this is the overall picture. I hope that I have made it clear to you. And now I will make the final diagram for the end of the course, and that should be enough. I don't think I have enough time left to teach anything more, say the uranium lead or the hafnium systems. It's not possible. So, I draw a diagram, and as before, I divide it into 4 parts. This is the bulk path. This is bulk path. This is the place, this is the plot of N mod. This is the plot of N mod, normal mod. Remember, in the last class or the class before, we were talking of normal mods in terms of rare earth elements, and we were not being able to express it. So I will not tell you the answer. I am just telling you this is where. Oh, sorry, I haven't given the coordinates. So, this is normal mob, and OIBs, ocean. I'm simplifying the diagram a little bit. So in different books you will see different plots. So generally this is ocean island basins. And here you have island arc basins. Also you have in these parts continental flood basins. Both OIBs and the continental flood basins, they plot here. And this is island arc basins. And then you have sure. And you get melts which are contaminated on this way. These are the melts that you get contaminated this way. There are sources, there are different ways in which, this depleted mantle business is a little more complicated. You have depleted mantle 1, depleted mantle 2, depleted mantle 3. There are different, thought to be different reservoirs of depleted mantle, but we don't go into that. It opens up a completely new Pandora's box. So what I am trying to do is, this is the plot of the N mob at the depleted mantle. All normal mobs plot at the depleted mantle. That means normal mobs are derived from melt extracted mantle. So that means the normal mob is a melt. It is extracted from a melt extracted mantle. So this is a two-stage melting process. Now I hope from the rear arcs you can combine the two. The ocean island basins and the continental flood basins, they are not plate margin basins, but they are intraplate basins. So they normally have over hotspots that occur right within the plates. And so what you have, this is the position of the ocean island basins and the continental flood basins. Although some continental flood basins are also found to extend this way, maybe they are contaminated with the continental crust. And the island arc basins, they form here, which is easy to understand because they are produced from partial melting of already existing crust, and so they fall here. Now this zone, this part, has a name. It's called the mantle array. The mantle array. So all mantle derived rocks occur in this way. These are melts and these are source rocks. Yes? So I think I will stop here at the moment. The most important points was I tried to improve upon your understanding of the theory through the course in understanding melt generation. What I tried to put things in a coherent way, that all this isotopic variation, large scale models, they are ultimately linked very much. This global scale phenomenon is related actually to angstrom scale processes that I told you before about packing, about radius ratios. It is about coordination numbers. It is about the type of bonding that characterizes. It's about spaces, and these scales are only a few angstroms. Several angstroms is the scale of this. Whereas the effect of all these processes that relate to large-scale global crust mantle differentiation, that is related to all those processes that are essentially controlled at sub-grain scale processes. This I thought that I do. And in the process, I wanted you to sort of, what should I say? So to better understand the theory and the logic rather than understanding it in a piecemeal. So I tried to combine crystallography, mineralogy, petrology, geochemistry. A lot can be said more about this if we add more isotope systems. But I think we don't have time, and your exams are 19, have to be held on 17th, I guess. So I think I have tried to do my best. Now I leave it to you. Thank you. Stay well.